So one of the things I need to talk about is how electrons at this point in hydrogen atoms and other atoms can move around between these different orbits. And so one of the things I kind of want to discuss is just looking at the example of hydrogen. So again, what I have on the screen here is I have a picture of hydrogen, and right now this hydrogen atom, because the electron's in the first orbit, is said to be in the ground state. And so that is going to be the most stable state of hydrogen because the electron has the lowest energy and the atom has the lowest energy. Now, the question is, how are these individual lines from a spectra produced? So let's say we stuck this hydrogen atom into a glass tube and we hit it with a lot of electricity. What could happen? So one of the things that could happen is that the electron can leave the first energy level and go out to a higher energy level where it'll have more energy. So in this example, we have the electron being sent out from the first energy level, or orbital number 1, to the third energy level, which is orbital number 3. Now the reason why it can go out to a higher energy is because the electron is absorbing energy from the electricity that it's being hit with. And so that can shove that electron into a further out orbit. This is the third orbit in this case. Another thing to kind of point out is when the electron is out in that further orbit, it is no longer in its ground state. It is in an excited state. Now, something important happens at this point. Let's say again we have this electron that is now been shoved out into the third orbit, which is relatively far away from the nucleus. It won't stay there for very long, maybe like a nanosecond or a picosecond. What will happen is that the electron will want to fall back to a more stable, lower energy orbit. And so in this example, which I have here, the electron was in the third orbit, but now it's falling back into the second orbit. And so because the electron in the second orbit has lower energy than it did when it was in the third orbit, it has to get rid of that excess energy somehow. The way it does it, the electron transfers its energy to a photon. And so that photon will have a specific frequency and a corresponding wavelength, and you will see it as a particular band in the line spectra. This sort of explains how you can see individual lines in a spectra when you excite a particular atom. So again, we have the example of hydrogen here, and we're trying to find an explanation as to why you have the particular lines at the wavelengths that they're seen in. So we have a red line at 657 nanometers, a blue-green line at 486 nanometers, and a violet line at 434 nanometers. And so you can sort of see that those lines correspond to where the electrons are going to when they fall back to a lower energy state. So what you can see is if you were to excite a hydrogen atom and knock up an electron to the third energy level, again, it won't stay there very long. It will fall almost immediately back to the second energy level, and it will release some energy. Now, what you can see is that that difference between the third and the second energy level is not that great, so that the energy that's releasing is going to be a relatively low frequency, which corresponds to a relatively great wavelength, which will be seen in the red at 657 nanometers. On the other hand, if you have an electron that receives enough energy so it's knocked up to the fourth energy level, again, it will not stay very long there, but it will fall back to a lower energy level, the second energy level. But this time is falling over a greater amount of energy. And so, if so, the energy of the photon is going to be much higher. It's going to have a higher frequency and therefore a lower wavelength, which will appear as blue-green or 486 nanometers. And then the final example there is where you have an electron that's knocked up to the fifth orbit or the fifth energy level hydrogen, and then when it falls back, it releases a much greater amount of energy in that photon, and so that energy will correspond to a certain frequency, which will be 434 nanometers. So this slide just kind of reminds us that if you have a hydrogen atom and it's just kind of sitting there, it's not being electrified, its single electron is going to be in the first energy level, and so that hydrogen atom is said to be in the ground state. But if you send electricity through it, what you can do is you can send that electron to a higher energy level where the electron will have more energy and the atom will have more energy when the electron's in the third energy level. So what must happen is the electron must absorb the energy so it can go into the higher energy level from the electricity. But again, once it's that relatively unstable higher energy level, it's not going to stay there very long. It'll fall back to a lower energy level. And when it does, if the electron goes to a place of lower energy, it's going to have to release that extra energy. And so that is what creates the photon of the specific frequency. Okay. What you're going to have to do is do problems where you're calculating the energy change of the electron or the atom when an electron moves between energy levels. And so I have an equation that will allow you to do that. So to use this equation, you will have to get the Rydberg constant, which will be on your test or on some kind of help sheet that you have. So the value of the Rydberg constant is 2.18 times 10 to the negative 18 joules. And then what you'll do is when you use this equation, you'll have to note what energy level the electron was at originally, which will be the initial energy level, which is symbolized by Ni, and then what is it going to in the end, and that will be the final energy level symbolized by Nf. And you'll have to square those and they'll be part of the denominators of fractions. You really can only use this equation for the hydrogen atom. This only seems to work well for hydrogen. With other elements, you can get results that are close, that could be explained by this equation, by changing the Rydberg constant slightly, but still you won't get a perfect match of the data from with other elements. So this only works really well with the hydrogen atom. Okay, so another thing that you may have to calculate is when the electron falls from a high energy level to a low energy level, it's going to release a certain amount of energy. And so what you're going to have to do is calculate the energy that is found in that photon and its corresponding frequency of the photon and the wavelength of the photon. And so I have a formula for that. So when you do calculate the energy change of the electron or the atom, if you take the absolute value of that, that should give you the energy of the photon that's released, and that'll have a corresponding frequency, which is symbolized by nu, and of course from that you can get the wavelength of the photon as well. So let's go ahead and do this practice problem here. A hydrogen atom absorbs enough energy so that its only electron at the first energy level is bumped up to the third energy level. Here it falls back down to the second energy level, releasing a photon of light. What is the A, energy change of the atom when the electron falls from the third energy level to the second energy level? B, the energy of the photon that is released during this change, and C, what is the wavelength of that photon? So to sort of help me understand this problem, what I'm going to do is make another drawing. So here, I'm going to just quickly draw the hydrogen atom again. Here we have the nucleus, and so here is the first orbit or first energy level of the hydrogen atom. Here is the second energy level of the hydrogen atom, and here is the third energy level of the hydrogen atom, which is the third orbit, if you want to think of it that way. So let's just use a different color pen for an electron. So what is going on here? So what is happening is that we have an electron here originally in the first orbit in the first energy level. So again, this electron would be said to be in the ground state of hydrogen. If you electrify this hydrogen, you can get these electrons to go up into higher energy levels or orbits. And so that's what's happening in this problem. The electron is moving up to the third orbit or the third energy level. And so again, here in this orbit, it'll have much higher energy than it had when it was in its first orbit. And so the way it got there was just taking in energy from the electricity. Now, as I kind of mentioned before, once it's in this higher energy level, it's not going to stay there very long. It's going to fall back to a more stable or lower energy level. And so in this problem, it's going back to the second energy level here. So when it does that, because it's going to go from a high energy state to a low energy state, that extra energy has to be released. So that energy goes off, and this will be the energy of the photon. And so this will have a corresponding frequency associated with it. Okay, so let's go ahead and solve part A of the problem first. And so part A, what we're trying to do is we're trying to find the energy change of the electron here, or the atom, when it goes from the third energy level to the second energy level. So that's part A. Okay, so here the formula you want to use is that the change of energy of the atom or the electron, you could say either one, is equal to negative of the Ribert constant over 1 over the final energy level it goes to squared over 1 over the initial energy level it starts from squared. And so what we can go ahead is figure that out. So it's delta E of the atom is equal to negative RH. And so what is the final energy level that this electron is going to? So it originally started out in the first energy level, right? But then it was knocked up to the third energy level. That's really where it's starting from in this problem. And then it's dropping to the second energy level. So that would be the final energy level. So it's going to be 2 is the final energy level squared. Now, what is the initial energy level? Again, just consider here we're looking at a transition when the electron is moving from the third energy level to the second energy level. So the initial energy level in this problem, because you're looking at transition from third to second, is going to be the third energy level. So that's going to be 3 squared. Anyway, if you solve this carefully, let's see what we get. So it's negative 2.18 times 10 to the negative 18 joules over 1 over 2 squared is 0.025 minus 1 over 3 squared, it's 1 divided by 9, and so I think that's 0.0111. Anyway, if you work this out, the number you should get is negative 3.03 times 10 to the negative 19 joules. Again, so what this negative energy is here, 3.03 times 10 to the negative 19 joules, this is a reference to the change of energy that an electron goes through as it falls from the third to the second energy level. And also it's the change of the energy of the hydrogen atom when that happens. Now, to solve part B, we just have to remember that any energy lost by the electron when it undergoes this transition will be gained by the photon. So what we do is remind ourselves that the energy of the photon is equal to the change of the energy of the atom. But importantly, any energy lost by electron must be gained by the photon, so we have to switch the signs. And so probably the easiest way to handle that is to just take the absolute value of the change of energy of the atom. And so what you can see is that we have the change of the energy of the atom is negative 3.03 times 10 to the negative 19 joules. You take the absolute value of that, that will give you the energy of the photon, which will be a positive number. And so generally when you're dealing with photons, you should have numbers that are positive. So the energy of the photon is equal to 3.03 times 10 to the negative 19 joules. Okay, so the final part of the problem I'm going to do over here, which isn't so bad, you already know how to do that. What is the wavelength of the photon in nanometers? Okay, so we have an energy for the photon, and so we have to convert that energy to a wavelength in nanometers. And so what I recall is that the energy of the photon is equal to Planck's constant times the frequency of the photon. And so what we have to do is we're going to have to figure out what the wavelength of the photon is. And so there are a number of ways you can do this. You can take the energy of the photon, put that number here. We have Planck's constant. You can solve for the frequency of the photon, and then you can put that into C is equal to nu, which is frequency, times lambda, which is wavelength, and solve for wavelength. That is one way you can do it. Another way you can do it is you can just create an equation that solves for the wavelength, the lambda. So that's what I'm going to do right now. So I also recall that the speed of light is equal to the frequency times the wavelength. And so this is true whether you're dealing with a lot of waves of light or whether you're dealing with one photon. So I could also say the speed of the photon, which is 3.00 times 10 to the 8 meters per second, is equal to the frequency of the photon times the wavelength of the photon. So anyway, let me just substitute that in. I'm just going to leave out photon at this point. So I get E is equal to H And so I'm going to solve this for V. So it's going to be C over lambda. That looks good. And so again, what we do is we want to solve for wavelength here. And so you can do a little algebraic manipulation. So it's going to be wavelength is going to be equal to Planck's constant h times the speed of light over the energy. So let me just go ahead and throw in those numbers and just confirm that units cancel out as we expect. So Planck's constant is 6.626 times 10 to the negative 34 joules times second. Speed of light is 3.00 times 10 to the 8 meters per second. And then you're going to divide it by the energy. And so the energy we get for the photon is going to be this positive value here, which is 3.03 times 10 to the negative 19 joules. And so the joules cancels out, the seconds cancels out, and so we get a wavelength in meters. And so what you'll have to do to finish off the problem is you'll have to take that value and convert the value you get in meters into nanometers. So I could continue this. You would have to take this number and multiply by some fraction to get this into nanometers. And so I think it would be 1 nanometer over 1 times 10 to the negative 9 meters. And that should give you the answer of 656 nanometers. So just to summarize this problem, if you take a hydrogen atom and you electrify it, the electron starts out in the first energy level. The electricity gives that electron energy, so it's knocked up into, in this problem, the third energy level. So one of the things we found was the energy lost by the electron and lost by the atom when it goes from third to the second energy level, and that's this negative value here of negative 3.03 times 10 to the negative 19 joules. That energy lost must be the energy gained by the photon. So it's the same number, but a positive value. And that is going to correspond to a particular frequency and wavelength of the photon. So we will now move on. Okay. So what I want to kind of point out here is you may have to figure out, given the values of energy levels that the electrons are transitioning between, can you figure out which of the transitions is going to release a photon with the most energy and which is going to release a photon with the least energy? So here's sort of a good example of that. So let's compare three examples here, three possibilities. First possibility is when the electron is in the second orbit or the second energy level and it's falling to the first orbit or first energy level. That's going to release some energy. Now, you're going to compare that to when the electron is in the third energy level falling to the first energy level, and you're also going to compare that to electron which is in the third energy level falling to the second energy level. So of those transitions, which one releases the most energy? In other words, it'll release a photon with the most energy, and which will release a photon with the least energy? And so I think you can sort of figure out pretty easily that the electron that's further out, say in the third energy level compared to the second energy level, if it's falling to the same energy level, which is the first energy level, then the one that's falling from the third energy level to the first energy level should release a photon of greater energy. And so the question is, of those transitions, which one releases a photon of lesser energy? And so you have to think about this a little bit more carefully, but you can sort of see from the diagram on the left, if the electron is falling from the third energy level to the second energy level, that is actually going to produce a photon of less energy than if you had an electron that is falling from the second energy level to the first energy level. And so there are the answers there. Now there's one more thing I want to mention, is you need to know the difference between two different kinds of line spectra. One is called an absorption spectra and one is called an emission spectra. And so I have some pictures here of two different kinds of spectra. And so in each of these pictures, what you can see, there's actually a mixture of a continuous spectra and a line spectra. But you can see that the top picture looks a little bit different than the bottom picture. So in the top picture, we have a continuous spectra, but kind of overlaid on it, we have a bright line spectra. If you see bright lines that are appearing in the spectra, and they may or may not be overlaid on a continuous spectra, the bright lines that you're seeing are something called an emission spectra. So the spectra below that is different. The lines are in exactly the same location, but instead you don't see bright lines. What you can see is that the lines are dark. And so if the lines are dark on this continuous spectra, then what you have here is something called an absorption spectra. So the question is, how do you get these two different kinds of spectra? So what is going on here is that you have some source, in both cases, of black body radiation. And it's the black body radiation that is creating the continuous spectra. Now, on top of that, maybe in this sample, so not only do you have the source of black body radiation, but you have some kind of purified element in the sample, and such that if the element is charged in the sample in a certain way, along with the black body radiation, those electrons in that element are being knocked up to a higher energy level, and then they're falling to a lower energy level. And that is creating the bright lines that you see, because when electrons fall from higher to lower energy levels, they're going to be releasing photons emitting light, and so you should see specific lines of particular wavelengths emitted. Now, with the absorption spectra, it must be created in a slightly different way. Here, maybe we have is a sample of black body radiation. And again, the black body radiation, like in the emission sample, is releasing a very broad spectrum of wavelengths. But here in this sample, again, maybe you have some kind of element that is absorbing these particular radiations that the black body source is emitting. Here, this particular element must be the same for the absorption spectrum as an emission spectrum, because whether you have lines that are being emitted or lines being absorbed, they're in exactly the same location. So it just suggests that the element is exactly the same. It's just that with the absorption spectra, the element is taking away energy from the continuous spectra and absorbing that. So thank you for listening to that, and we will see you next time.